Problem 10.11. A consumer organisation is concerned about the increase in the level of credit card debt of young customers. It commissions two surveys in October 2004 and October 2008 of 1,000 consumers aged 18 to 24 years old. Okay, so we're starting off this problem with a bit of background information as to what's motivating our surveys. The key information at this point is that we've taken two surveys. So we've got two sets of sample data relating to October 2004 and October 2008. So this is quite important because it tells us that we're going to be doing two samples, which is therefore two populations. Okay, so if we keep going with the question information, these show an average credit card debt of $5,800 in October 2004 with a standard deviation of 960, compared with an average of $6,320 in October 2008 with a standard deviation of $941. So clearly we've got two samples. If we look at Part A specifically, we're told, assuming that the population variances from both years are equal, is there significant evidence that the mean credit card debt is higher in October 2008 than in October 2004, and we've got to use a 5% level of significance. So we've been asked to do a hypothesis test. As we said, we've got two samples, therefore we're testing two populations. Our two samples provide the evidence. Now we know that the first thing to think about with any two population hypothesis test is which population we're going to make population 1 and which one population 2. Now it doesn't really matter which way around you go, so long as you're consistent you'll end up with the same final conclusion when we link it back to the actual scenario. So what I've done here is I've said let population 1 be our October 2008 result and population 2 will be October 2004. Now remember, the null hypothesis is the status quo hypothesis. The alternative is the hypothesis of change. So it's the alternative that we're usually stating in our questions. So if we're trying to see that whether the mean credit card debt is higher in October 2008 than October 2004, the fact that we're talking about higher suggests that direction is important. So it's going to be a one-tailed test. We're testing means. We're looking to see if there's, the mean credit card debt is higher for 2008 than 2004. So if population 1 is 2008, we're looking in the alternative to see whether mu1 is greater than mu2. Mu2 representing the mean from October 2004. So that's our alternative. We can then work backwards and say, well, the complement must be the null. So the status quo is that mu1 is less than or equal to mu2. So mu1 less than or equal to mu2 can be rewritten as mu1 minus mu2 less than or equal to 0, and therefore in the alternative we have that the difference of means, mu1 minus mu2, is greater than 0. So what else do we need to think about? Well, whenever we're doing a two population test for means, we need to think about whether the variances for the population are going to be assumed equal or assumed not equal. So we've been told in the question that our population variances from both years are equal. So that means we're going to be doing the pooled variance t-test. Now that of course affects our test statistic calculation. It's a t-test, so it's a t-distribution, and we have our test statistic formula for this particular two population test of the means, and we'll see that on the next slide. Now, having set up the null, the alternative, and the level of significance, and having decided the distribution and specifically what test we're applying here, my next step is to draw up the decision diagram. Now, as we said, it's a t-test, so I draw up my t-decision diagram. I know from the null and the alternative, because direction was important, it's an inequalities hypothesis test, which tells me it's a one-tail, so I only have the one reject region. I can mark that onto my decision diagram. Now the trick with a one-tail reject region is we've got to think about whether it's a lower tail reject region or an upper tail reject region. And the way we tell is by looking at the direction of the alternative hypothesis. The only way we will go against the null is if our mu1 minus mu2, or our sample evidence from those populations, is greater than 0. So we're looking at an upper tail reject region. Remember, when it's one tail, the reject region goes in the same direction as the alternative hypothesis. So we've got an upper tail reject region. It's 5% in size. We know it's a t distribution. To find the actual critical value, so the cutoff point for that reject region, I need to use my t-tables, and that means working out the degrees of freedom. Now the degrees of freedom in this particular test, we've got n1 plus n2 minus 2. So add the two sample sizes together, subtract 2, we end up with degrees of freedom of 1,998. Now if you have a look at your t-tables, remember we've said that when you're doing the t-distribution, you go to the right row for the degrees of freedom, and then you can look up the critical value. Now we don't have a row for 1,998 degrees of freedom, so we've got to do some rounding. And we'll round that degrees of freedom off to 120. And if we have a look at the 120 degrees of freedom row in our t-tables, if we look up at the column for a 5% upper tail, we get a cutoff of 1.6577. So that's our decision diagram. We've got our reject region. Now we can calculate the test statistic, make a decision. Now, once you know that you're doing this pooled variance t-test, you might as well write down the test statistic formula. That's a good place to start. Yes, it's a little bit computationally intensive, but it's just a matter of being really careful. Now our test statistic is still of the basic format, point estimate minus population result divided by standard error. It just happens that in this case our standard error involves an SP squared term, and so we'll need to work that out first before we can calculate the test statistic. And you can see that just below I've done my separate calculation for SP squared. It's going to be n1 minus 1 times s1 squared, so sample variance 1 squared, plus n2 minus 1 times sample variance for sample 2. And then we divide all of that by n1 minus 1 plus n2 minus 1. Putting in all the numbers, remember our sample size minus 1, in this case for both samples it's 999. I've got my sample 1 standard deviation, 941, so I can square that to get the variance. My sample standard deviation for sample 2 is 960, square that. Pretty much at this stage, once you've written down all the numbers, it's just a matter of doing the number crunching, and we end up with 903,540.5. So having got SP squared, we can substitute that into our test statistic formula along with our sample mean 1 and sample mean 2. Now keep in mind for mu1 and mu2, we've got that mu1 minus mu2 component. When we do a hypothesis test, we proceed on the basis that the null hypothesis is true. If the null hypothesis is true, mu1 minus mu2 is equal to 0. So put in all the values and do the calculation on your calculator. Probably do the square root component separately, just to make sure that you don't have any calculator error. And we come up with a test statistic of 12.232. Okay, so having got our test statistic, the last step is just to compare that to the decision diagram, and we can see that it's clearly in the upper tail reject region. So we reject the null, and we can write our conclusion in terms of the alternative. So this is where we link it back to the actual scenario. We can say that there is sufficient evidence to conclude that the mean credit card debt in October 2008 is higher than October 2004. So Doesn't matter which way around you have your populations, once you get to the final decision and you turn it into words, you end up with a consistent decision.